All right, can everyone see my screen? Excellent, I'll get started then. Well, good afternoon, everyone, and thank you to all for joining today's workshop. I specifically want to thank Madi and Dong Yang and Purdue and everyone for making this event possible. My name is Sarah Kreikemeier, and I am a senior mechanical engineer at IonQ, and I am just thrilled to have the opportunity to speak about IonQ's quantum computing systems, as Madi said, on the hardware side of things, and get into the details of the technology with everyone today. So today's presentation is going to start at the 100,000-foot overview of computing, a lot of similar overlap to what Madi talked about with Moore's law, and then dive into the nuances of the various systems that make up IonQ's quantum computers. So we'll start off with a short segment on classical versus quantum computing, ultimately just as a segue then to discuss the trapped ion architecture, which IonQ uses for its quantum systems. And then the majority of this presentation will dive into the details of the hardware, which involve the optomechanical systems, the control electronic systems, and then the software systems that all work in concert to power IonQ's quantum computer. And then I'll just wrap up with a few details about IonQ as a company and some of our capabilities, because I know that the club has access to IonQ's hardware, and so just want to talk a little bit about some of the capabilities. So a little bit about me. I have been with IonQ for the past 4 years, working as a mechanical engineer on the hardware team. And I've been incredibly lucky to work on many aspects of the hardware design, from the large enclosure, which I will show later on in the presentation, all the way down to custom optomechanical assemblies that can fit in the palm of your hand. I work on most aspects of the system design through their entire life cycle, so that starts at high-level system requirements, basically starting at the atoms and the ions, then going into subsystem, ultimately down to component requirements, then transitioning into detailed design work, which involves analysis, testing, iteration. Ultimately, when the designs are done, we move into procurement, assembly, characterization, then ultimately deploying these systems into the computer. And so my focus over the past year specifically has been very much in the optomechanical realm. And so while optical systems are in IonQ's computers, the mechanisms which enable quantum behavior of the computer, you'll see that this presentation does go into a reasonable amount of detail about those optomechanical requirements and constraints. Prior to joining IonQ, I worked briefly at a healthcare company in the Bay Area, and my undergraduate degree is in mechanical engineering and business from University of Virginia. In my free time, I love creating art, whether that's painting, drawing, playing music on guitar or banjo, and then just staying active. So this is similar to kind of what Madi was talking about with Moore's law. Let's take a look at where classical computing is today. The example of the traveling salesman problem is a great one for quantum computing, in that there are some problems that classical computers just cannot solve in a finite amount of time. And those are problems with many, many different variables that all impact one another. So you can think of either the traveling salesman problem, or say a financial forecasting model that has tens of thousands of interdependent variables. The time to perfectly model all of the complex interactions and optimize those for all variables just cannot be completed without either imperfect approximations or just not being able to complete the problem with today's computing problem. So as many of you know, Moore's law describes how computing power doubles roughly every 2 years, ultimately as a function of how many transistors can be fit on a single chip. And for the sake of not repeating too much information, and as transistors get smaller, you get closer to the size of an atom, and they don't behave classically. And so Richard Feynman said famously in 1959 that there are these really unique opportunities for designing circuitry when you operate with atoms at a small scale. So basically, the properties of quantum mechanics that exist at this subatomic level can be exploited for significant advancements in computing. So most of the audience today is probably familiar with the elements of classical computation. The fundamental unit of information is the bit, which is represented by either a 0 or a 1. And quantum computing differs from classical computing in that the fundamental unit, known as the qubit, can be a 0, 1, or this complex combination of both at the same time, which is known as superposition. And superposition is one of the elements of quantum mechanics that is really important for enabling quantum computers to perform the way that they do. So classical computing bits on one hand are discrete, while quantum bits on the other hand are continuous. And so this continuous representation of the state of the bit is represented by what's called a block sphere, which you can see on the screen with this spherical image. The north and south pole represent the pure states of either 0 or 1, and then the interior points, which are represented by a vector that goes from the center of the sphere to the surface, represent the mixed stages, which basically it's the superposition states of 0 and 1. And essentially it's a polar representation of that complex number, which is the superposition quantum state. So the ability of the fundamental computing unit in a quantum computer to be both a 0 and a 1 simultaneously allows for the quantum computer to have exponentially larger computing capacity than its classical counterparts. And so the true power of quantum, we talked about superposition, that's one aspect. The real power is in actually the interaction between qubits, which is known as entanglement. And so at a very basic level, entanglement ties the information between one qubit to another. And it's what makes qubits more powerful in storing and calculating information compared to classical bits, which are not only discrete, but they cannot be tied to other bits in the circuit. And so quantum computing as a result is then very well suited for problems that involve parallel computation or optimization problems like the traveling salesman problem. So the bits in classical computers are physically represented by small amounts of electrical current, which are combined in transistors to create gates and to run calculations. In the architecture and the structure that IonQ uses for trapped ions, the qubits are individual atoms, and they are combined in the same way that electrical currents are combined in transistors by laser beam interactions, which basically input states onto those ions. And that is what allows the gates to be run and calculations to be completed. And so what makes trapped ion quantum computing architectures unique in comparison to classical computing or even superconducting quantum architectures is the reconfigurability of the circuits. So because we're shooting individual laser beams at ions, you can choose which lasers you turn on and which ions you point to. And that's analogous loosely to, in the classical world, a field programmable gate array and how we can tune for different applications without needing to change the hardware. You basically just rewrite the firmware or the software and you have the fundamental architecture that can be very scalable or reconfigurable. So considering the limitations of Moore's law today and today's classical computers and their computing power, you might be wondering what's next. So in order to revolutionize computing, there needs to be this paradigm shift to kind of step away from the classical realm and move into the quantum realm. At IonQ, we are developing powerful and scalable quantum computing systems, which use individual isolated atoms as their fundamental computing bits. And so in this presentation, I'm going to be getting into the details of how IonQ uses trapped ions for its quantum processors. So before getting into the subsystems at a very conceptual level, I want to kind of take a step back and look at this picture of an old ion trap lab. Not everyone on this call is familiar with what an ion trap quantum system looks like. And I like to show this photo because it's kind of crazy. It's maybe 10 years old and it's from the lab of Chris Monroe, who is one of IonQ's co-founders. So for scale, you have a few grad students and the room is maybe 10 meters in length along into the screen direction. And so this photo contains all of the things that are necessary to build a trapped ion quantum computer, both from the hardware side of things, but then also the folks that build it and run it. And so by the end of this presentation, my goal is to get you familiar with the different aspects of this system and how we've kind of moved from this lab environment to something that's much more commercial. So I like to start when talking about IonQ systems by first focusing on the ions, which are the heart of the quantum computer. They are controlled and configured by IonQ's custom ion traps, which you see an image of on the screen. And for a number of reasons, ions are highly desirable for building a quantum computing architecture. For one, all qubits are exactly identical to one another, which is beneficial for the interchangeability of qubits if we want to add qubits onto the chain or swap qubits in and out, as well as the repeatability, reliability, and ultimately the performance of the quantum computations that can be run with these bits, because inherently they're perfect. We call them nature's qubits. And then once ions are prepared in a stable state, which is a term that I will go into more detail on with the optical systems, the ions remain in this state for a very long time. So they're consistent and they're stable, and that's hugely important as algorithms are run over long periods of time. They need to be reliable. And this consistency is one of the drivers for one of the most reliable atomic clocks that uses ions. The image shown on the screen is of IonQ's trapped package, which is highly scalable in terms of the number of high-performing qubits that can be used. The performance, I want to take a little pause here because the performance of a quantum computer is not entirely tied just to the number of qubits that your system has, but rather in the performance and the quality of those qubits in their own right, and how easily entangled they can be with other qubits for a given calculation. And so at IonQ, we use a term that is called algorithmic qubits to kind of give a proxy for not only the number of qubits we have, but how high performance they are and how well they can be connected with other qubits in the system. And so that is, I'm not going to get too much into the physics behind all of that, but it's not just about how many qubits you have. So the bow tie image on the screen is of the ion trap. And if you look at the center, there's this glowing piece, which is the quantum zone. And above that quantum zone, we can load many chains of ions. We can separate them and merge them with really high reliability. And you might be wondering, what does this mean? What do other ion traps look like? Basically, it allows for more high quality ions to be loaded on a chip without performance losses because they can be moved around in such a repeatable and reliable way. And ultimately, the goal is to network multiple sets of chains together to then further increase the computing power of the systems. So now that we've looked at the ion trap, we can take a step outwards and start looking at the optical systems that are needed for trapping an ion. So at the heart of the computer, the quantum computer, is the vacuum chamber. And inside of that vacuum chamber is the ion trap. Now, the vacuum chamber has a number of optical viewports so that different laser beams can be aligned to the ion trap. And these laser beams are used for the various processes needed to run a quantum algorithm. So basically, a quantum computer or trapped ion quantum computer requires three main optical subsystems. And when I say optical subsystems, I'm referring to laser beam systems that deliver beams and interface with the ion trap inside of the chamber. And these optical systems must be precisely aligned and controlled using sophisticated software, electronics, and control systems. And ultimately, the harmony of the hardware with the software is what enables high fidelity quantum algorithms. And so the structure of this presentation breaks out optical, control electronics, and software, but please understand that this is something that is very tightly meshed and highly integrated. So the first system is known as the ion initialization system, and its purpose is to load ions in the trap, prepare the qubits for the quantum computations that will be run. And it's also responsible for creating the ions, cooling them, which I'll get into detail on that, and finally preparing the qubit states so that they're initialized all at the same atomic energy level prior to the computation. The second subsystem is known as the gate computation subsystem. Once the qubits are loaded and initialized in their ground energy states, laser beams from the subsystem are used to precisely manipulate the qubits' energy states. And qubits are used to store information that is essentially encoded by the laser beams. And then finally, the computation readout system is used to collapse the states of the qubits in order to read out the quantum information that they were storing. And this system relies on photons from the qubits to read out their state. The stability of all of these optical systems is essential for high performance of the quantum computer, and the system as a whole must be robust to any types of external disturbances like vibrations, thermal gradients, acoustics, and a lot of design and analysis goes into stabilizing and building these systems. So jumping into more details about the ion initialization system, the ion trap and its connected structures are installed inside of an ultra-high vacuum chamber, which further isolates the ions from the environment. And for the sake of time, I'm not going to get into the details of ultra-high vacuum, but just know that it provides a very stable environment that is clean and free of noise for the ion trap. We ionize ytterbium atoms to produce our qubits. And so in order to ionize a ytterbium atom, a laser enters the vacuum chamber through a viewport and then strips an outer electron from the atom. This is known as ionization. And for context, all of this is occurring right above the surface of the ion trap, which is at the center of the vacuum chamber, roughly. Now, once the electron is stripped away, the atom is ionized and positively charged. And beyond using ytterbium, which I pointed out on this slide, we recently announced our plans to use barium as another qubit variation for our computers. Because the qubits are positively charged, they're able to be held over the ion trap using electromagnetic fields. And I'll be getting into some more details about how this works on the control electronics and software side, but basically to visualize how the electromagnetic fields hold the ions in free space, I want to focus on the images in the upper right corner of the slide. So imagine a tennis ball sitting on a saddle. If the saddle spins around really, really fast, the tennis ball can't roll off the sides. And so the same principles are applied at a much, much smaller scale with electrodes in an ion trap to hold many qubits in an ion chain. Once the ion chain has been loaded, lasers with precisely tuned wavelengths and frequencies are aimed at the chain for Doppler cooling. And this is used to freeze. I'm putting this in quotations because we're not referring to dilution refrigerators or near 0 Kelvin temperatures. I'm talking about freezing the energy of the motion of the ions. We want them to be perfectly still on an atomic level. So in order to visualize Doppler cooling, imagine trying to stop a kicked soccer ball heading through the air by throwing tons and tons of tennis balls at it from the opposite direction. Basically, the laser beams from Doppler cooling function as the tennis balls that impede the motion of the soccer ball, which is represented or represents the ion. And then additional lasers are used to modify the energy states of the qubits, so they're all initiated at 0, and this process is known as optical pumping. Pivot to the gate computation subsystem. After an ion chain is trapped and initialized, quantum algorithms can be run. And so for this optical system, laser beams are specifically tuned to excite the ytterbium qubits from their ground energy state to their excited energy state. So individually addressing beams focus on single ions, while global beam simultaneously shines across the entire chain. They're coming in from opposite directions. The interference pattern of these two overlapping light waves allows the qubit's energy states to be manipulated. And I'm not going to get into the atomic and molecular physics, so just trust me on this at this high level that we're discussing it. So any phase difference between the interfering beams degrades the quality of the quantum computations. And so that's an important note that I'm going to cover in a little bit more detail in an upcoming slide. So I often think of the quantum algorithm as playing a song on a harp, where each string is a qubit, and by playing multiple strings together and producing a chord or a unique sound, you're combining the vibrations of the strings. And the analogy here is that the vibration of the strings are the micro motions of the ions that then get entangled to one another. And so ultimately the song that gets played on the harp with plucking all of these different strings together is the quantum algorithm that's run. And so one benefit of using the trapped ion approach is what we call the complete connectivity between qubits in the ion chain. And so I mentioned this when comparing classical circuitry FPGAs with trapped ion quantum architectures. Basically, every qubit is able to interact with every other qubit because they're not physically wired to one another. And so that's what this graphic shows in the top right corner of the slide. You can have connections made between every single qubit in your chain. And that's because of the individual addressing with the laser beams and the control systems that allow that type of interaction. Ultimately, this means that trapped ion quantum computers don't need to have as many qubits compared to a less connected qubit architecture, and this produces higher fidelity results. All right, so now we're going to go to the last system, which is the computation readout subsystem. Once the algorithm is completed, the result of the computation is read by shining a laser across the entire chain and then measuring the light that is emitted by each qubit. Shining the resonant laser collapses the quantum information stored by the qubits and then forces them into a 0, ground, or 1, excited and glowing energy state. So the qubits with the excited energy states produce more photons that can be measured by a detector. And one of the challenges that's associated with this type of system is the collection of light from the ion chain. So as a result, the system needs to be very precisely aligned to collect as much light as possible. And there are a lot of clever tricks that can be used to do this. So now that we've gone through the optical modules for trapped ion quantum computers, I'm going to transition to some of the challenges associated with optical systems before transitioning to the control and electronics and software. So each beam entering the vacuum chamber must maintain pointing stability, intensity stability, and beam quality. And these factors are necessary for high fidelity quantum operations. So misalignment, also known as pointing errors of the beam, must be minimized so that the beam is actually shining precisely on the ion. We're talking about ions, they're very small. And so having both the position and the angle properly tuned so that you have perfectly overlapping paths is critical. The beam power, also known as intensity, must be stabilized. And lastly, the beam should not have any optical quality issues that arise from imperfections in the delivery systems. So examples would include wavefront errors, astigmatism, defocus, just to name a few. So if you've been counting, there have been 6 different beams that enter the vacuum chamber and that are aligned to the ion chain. And in a perfect world, the incoming beams would not have any interaction with the environment. It'd be like a cow in a vacuum, and they'd have perfect stability and quality. But the reality is optomechanical elements and supporting mechanical infrastructure are needed to deliver the beams from the lasers, ultimately to the ion trap in the vacuum chamber. So as a result, the optomechanical design seeks to perfect pointing stability, intensity stability, and beam quality. Now that we've discussed the optical requirements of a single beam, I would like to discuss the requirements of the 2 beam paths from the gate computation system that overlap at the ion. The global and the individual beam paths point at the ions from opposite directions, and the resulting interference pattern between those 2 light waves must be kept very stable. This is known as interferometric stability, and it's determined by phase differences between those light waves. So misalignment of the beams degrades the stability if they're not both pointing at the ion. Any wavelength changes in the laser beams due to the laser output instability impacts both the phase and the frequency of that interference pattern. And then of course, optical path length changes as the beam gets delivered through the systems and comes to the ion lead to micron level disturbances, which again impact the phase of those overlapped beams. And so the interferometric stability of 2 beams leads to improved quality of quantum computations for trapped ion systems. And as a result, the optomechanical design and systems seek to optimize interferometric stability. Now, after looking at the different subsystems on a conceptual level, you might be wondering what an actual optomechanical system looks like. And so this slide highlights a few different architectures. The left image is a lens assembly like you might see on a camera, telescope, pair of binoculars, and then the right image focuses on beam ray tracing through free space optics, which have lenses, mirrors, beam splitter cubes, irises. And fundamentally, the design of either of these types of architectures starts with the various optical pieces that convert the beam output from the laser into the properties and the configurability that are required by the ions. So when I say properties, I want you to think, what's the beam diameter? How far apart are the ions? How many ions are there? How should we address them? And so the optical elements kind of convert a laser output, which is standard, to what you need at the ions. Now, imagine those optics are floating in free space. It's then the optomechanical design to mount these, adjust them, and then isolate them from environmental disturbances and give the necessary degrees of freedom that allow for the software and electronic systems to do optimization, automation, and calibration. Now recall, at the heart of the quantum computer are the ions, and the various lasers must be precisely aligned to those ions in order to control them and produce the high-performing systems. This is why there's such an involved focus on optomechanical design considerations, because fundamentally the optical systems are what are implementing the quantum mechanics of the computer. And so ions are very small, they're very sensitive to disturbances, and the precision of the beam at the ion level is on the order of microns. It's highly precise. And so when designing these systems, there are a lot of questions to consider. I'm not going to get into all of them, but basically at the end of the day, like, how do you design for performance, for scalability, and for reliability? Once the high-level goals and requirements are finalized, the design process for these complex systems involves a lot of handshaking between all of the different engineers, but most specifically between the optical and the mechanical side of things. And so there's a prescription that gets determined by the optical engineer that says these elements will be used to convert the beam to how you want it at the ion. And then the engineer, the mechanical engineer, goes back and starts thinking about what knobs need to be turned, what kind of tolerance needs to be done, what kind of dimensioning, what materials, everything basically is in pursuit of high fidelity operations. And so there are many ways to distill those high level requirements down into how the subsystems are built. And so throughout this design process, it's very important to identify which subsystems in which elements in those subsystems are most sensitive, because it helps inform which design architectures to use. And so maybe on the previous slide, you want to have that free space setup. Maybe you want to have it in a subcell. Maybe you want it in caged optics. There are various ways to implement and mount the different optical elements. And so that's why this, there are a lot of considerations and a lot of back and forth when assessing the most critical elements of the system. And so ultimately, the goal of the optomechanical design is to minimize what we call noise sources in the optical system, such as vibrations, acoustics, temperature fluctuations, anything that degrades the optical performance, because that directly impacts the fidelity of the operations in the quantum computer. And so there are two approaches to this goal, and they're definitely not mutually exclusive. You can reduce the transmission of noise sources, such as using active vibration isolators, or you can reduce the system's sensitivity to noise sources, such as matching coefficients of thermal expansion. The second is much more of a design philosophy, but both are important when doing design. And so I've listed some best practices. Of course, it's not all inclusive and it's very much dependent on application, but this is just a list of considerations that often factor in. So now I spent a lot of time diving into the nuances and the details of the optical systems, which make the quantum mechanics at the ion possible. However, without the control electronics and the software, there would be no way to control, monitor, optimize, really do anything with optical subsystems, which are needed to do the preparation, manipulation, and readout of the qubits. So in the realm of control electronics, there are three main areas of focus. You have hardware design, FPGA firmware, and production. Hardware design focuses on building the circuits, both analog and digital, designing them into boards, and then integrating the boards with various other components and housings and interfaces. The FPGA firmware focuses on implementing and programming control loops and logic that pair with various components in the optomechanical systems. So to kind of make that less wordy, I want you to think of a lens in an optical system that needs to be dynamically adjusted based on intensity measurements of the beam somewhere that are a proxy for performance of the system. The FPGA firmware would then come into play. And so this whole area of FPGA firmware encompasses the digital to analog, analog to digital conversions, as the signals are passed between the hardware electronics and the control systems. And then lastly, production focuses on planning for upcoming development efforts, managing materials and fabrication, and then ultimately testing, characterizing, and deploying the control electronics in the systems. And so PCB fab is one of the common elements of production. And so there are a number of things to consider when designing and fabricating a PCB. One of those is working with the fab house to make sure that they can meet your specifications, weighing material considerations to ensure that the board is in acceptable environment conditions. Is it possible to assemble this board in-house, or does the fab need to do that? Where does the board go when it arrives? Is it going to be in a larger chassis interfacing with other electronics? Are there custom cables that are needed? A lot goes into production that then factors back into design. So it's this back and forth kind of play. It's not all just designing circuits. And so you may notice that the various functions of the control electronics, software, and hardware all have considerable overlap. And so this is representative of just the engineering development work at IonQ is highly cross-functional and collaborative. This diagram provides a simplified outline of the system architecture. So we've already gone into the optical systems. We can now see how the control architecture plays into those systems. And while not explicitly shown, I like to think about the software as the web that connects all of the nodes of the system and is completely pervasive. Of course, the orange arrows can be your software lines that run or your cables, but software is just pervasive and everywhere in how we run our systems. And so I'm going to go into a little bit more detail about the pulsar subsystem, coherent subsystem, and then the trap RF subsystem. The pulsar is the main control system, and it controls the trap digital to analog converter, the trap RF, and the coherent subsystem, as well as other ones that are minor and not listed. And with software, it provides the real-time control across all systems. So the signals sent out by this system are used for automation, and in order to rapidly move between jobs of sending out signals to different, kind of like the motherboard sending out signals to other boards, this system uses high-speed RF switches. And so clocking and timing concerns are exceptionally important. So for example, if the pulsar system needs to modify the coherent program to change its parameters for updated automation, it would use FPGAs and DDSs to have real-time high-speed communication with high-quality signals to interface with all the different areas. And ultimately, I like to think about the pulsar as the conductor and communicator with many of the connected control systems. The coherent subsystem helps create waveforms for the laser, and those are used to control the gates. So I want you to think back to the analogy of the harp and plucking the different strings to create a song. This was the analogy for how gates are run and how trapped ions are excited using lasers. The coherent system are the hands that play the harp and control how and when different lasers shine on different ions over the duration of the algorithm. Because radio frequency signals are needed, the phase, amplitude, and frequency must be precisely controlled with very high signal to noise, hence the need for direct digital synthesizers, DDSs. And then ultimately, the firmware, electronics, and the receiving device rely on digital to analog converters in addition to the FPGAs and DDSs to allow the system to operate. So this is just an example of how both the control electronics and the software are used to change the frequency of the laser beam using an acousto-optic modulator, or AOM. So basically the AOM is a device that receives a laser input beam, and the frequency of that beam as it exits the device is modified based on the RF signals which are sent from the coherent system to the AOM. And ultimately that impacts how we tune and adjust things at the ion. Now remember, the pulsar is at the top telling the coherent system to do this. The digital instructions include amplitude, frequency, and phase information. And this is in what I call software land, or the digital world. And then those are converted by low noise custom digital to analog controllers. And that then directly interfaces with the hardware. The trap deck and the trap RF systems send voltages to the ion trap to allow it to create the electromagnetic fields that trap the ions. And just for the sake of time, given that we looked at this tennis ball on saddle analogy, the trap RF system ultimately is what allows the electromagnetic voltage fields to be spun very, very quickly and to hold the ions in the trap. And so the images here kind of show the breakdown of electrodes on the trap and then this spinning saddle function that holds ion chains. Now, software is tightly coupled in all areas of hardware and electronics, and I'm just going to briefly summarize that here. So software is the orchestrator of all hardware, which basically consists of the optomechanical and the control electronic systems. And so software keeps the system tuned with device calibrations and stabilization. This includes tuning for ion trap fields, aligning beams to the ions, and then correcting for any drifts or transients in the system between jobs. Now, once there are ions, the lasers need to be calibrated. And a simple analogy to understand what it means to calibrate lasers: if I want my flashlight to shine on you as you enter a dark room, it's a lot easier for me to wait until you're already in the room and then sweep the flashlight around to find you, rather than to make sure you enter the room in the exact same position every time. So in this analogy, you entering the room are the ion entering the trap. And of course, the flashlight is the laser beam, which is used for all of the state preparation, gate computation, all of the different things that we talked about previously. Now, compiling circuits involves implementing different quantum gate types and then managing configurations of qubits in the ion trap. And so there's extensive software effort that goes into this, which I won't get into, again, for the sake of time and my lack of deep expertise in that area. Then once ions are loaded and calibrated, jobs can be run So running jobs requires what's known as pulse shaping for the gate computation system for tuning the laser interaction with the ion. So think back to the AOM that I talked about. You're sending in a sinusoidal signal to tune how the beam is adjusted. This is an example of pulse shaping that's done for the different elements of the quantum algorithm. And so basically the quantum circuits are a series of gates which are coded as those analog sinusoidal waveforms. Then finally, software is used to read out the state measurements after the computation is completed, return the system to idle, and then load a whole new series of analog waveforms for the next job. And so I like the image at the bottom right, which visualizes how the whole alignment process works. The left graphic shows individual beams which are grossly misaligned from the ions, which you kind of see from those dashed white lines. But using classical optimization allows you to adjust the beam position and the angle to optimize alignment to the ions. And there's a proxy and a measurement tool that takes data that then feeds into control loops, which uses software and controls and ultimately comes back to the hardware. So as I mentioned before, software is pervasive throughout the system and involves many different languages for the different functionalities. I'm not going to read through this list, but it gives context to what our software stack involves. Now, remember the image of the ion trap lab. This is an actual image of one of IonQ's quantum computers. Building the trapped ion quantum computer still involves many of the same elements that you saw in the old UMD lab photo, but what's changed between now and then is the development work to scale this technology to make it available to users like people here and to solve increasingly complex computations. So we spent a lot of time looking at the details of the engineering required for IonQ's quantum processors, but just taking a step back, IonQ's mission is to build the best quantum computers to solve the world's most complicated problems. The trapped ion architecture is crucial for high performance, for scalability, and for full connectivity. After decades of research, the company was founded in 2015 by Jungsang Kim and Chris Monroe, and we've since grown to almost 100 employees. The headquarters is in College Park, Maryland, and we are hiring. In October of last year, we were listed on the New York Stock Exchange and became the first publicly traded hardware and software company in the quantum computing space. IonQ is also the only hardware system that is available with all major cloud providers, which include Amazon Web Services, Google Cloud, and Microsoft Azure. There have been a lot of exciting developments recently, specifically with our recent announcement about the barium qubit technology, which I mentioned previously, and I encourage everyone to check out our latest press releases and look at more details about our technology roadmap, because there's a lot of exciting stuff that comes out, which feels like, almost on a weekly basis, you see these exciting announcements. And so before I wrap up, I do want to touch on some applications that can be made possible with quantum computing. IonQ recently partnered with Hyundai on their initiative to develop new variational quantum eigensolver, VGE, algorithms to study lithium compounds and their chemical reactions involved in battery chemistry. A lot of words. Basically, chemistry simulation is expected to improve the next generation of batteries by improving their charge and discharge cycles, with the goal then as improved performance, cost, and safety of those batteries in electric vehicles. And so quantum computing is best suited for chemistry problems because it exactly simulates the quantum mechanical phenomena that occur with chemical interactions. And so any simulation that's done at this level on a classical system is just an approximation. And so the pharmaceutical industry is very similar to the battery chemistry application because they're both looking at molecular interactions, and those interactions are comprised of quantum mechanical behaviors. There's no better way to simulate this than actually using quantum mechanical mechanisms in a quantum computer. And so the pharmaceutical industry can similarly benefit from quantum computers with the improved capabilities that could help facilitate drug discovery on much faster timescales without long clinical trials or error-prone modeling if there was a desire to model the chemical interactions. In the financial realm, IonQ released a paper in collaboration with the Fidelity Center for Applied Technology to demonstrate how its quantum computers can outperform classical computers in generating high quality data, which is then used for testing the classical models. And so it was found that the quantum machine learning algorithms that validated the financial models performed exponentially better than the classical counterparts. The bottom line basically is that quantum computing can lead to superior financial modeling And the principles of this work can essentially be applied to any industry that deals with complex systems with many correlated variables. And then because quantum machine learning was used in this fidelity paper, other applications that use classical machine learning could benefit from quantum machine learning as well. And so that could be self-driving cars and other smart robots. Lastly, here is a picture of the team in New York when we rang the opening bell on the New York Stock Exchange on the day of our IPO. It was a really wonderful opportunity for the whole team to go up to Manhattan and stand on the stock exchange floor to celebrate the years of hard work and the shared success. So just wanted to share that before wrapping up. And with that, I want to thank you all for your attention and interest. And if there is time, I know that we've got another presentation coming up at 1. Maybe we can take 1 or 2 questions.
Thank you so much, Sarah.
For the technical talk. If you have any questions for now, we can take them within like 5-10 minutes, or we can just switch to the virtual questions too, if you don't have any. That's the Q&A session. So for now, for the questions to Sarah.
So feel free to ask any question you have. So I think what Sarah covered was more about the hardware side of the IonQ platform to build the quantum computer, and they have made great progress in that sense. And this is not the only platform. There are other platforms out there. You can build these single atom transistors that I mentioned. And this is literally a single ion transistor. They're building many of these. And Sarah mentioned a lot of interesting applications out there and a lot of engineering challenges. And I'm sure some of you have come from the engineering background, and you can see how you can contribute to some of the challenges that they have in the technology. But if there's any question on the software, on the hardware, or how to get to this industry, please feel free to ask Sarah, and I'm sure she would be happy to answer that.
Limiting factor for getting more prevalent in the industry, or see that more people experience the economic side of this?
Yes, I think, did you hear, Sarah?
Were you able to hear the question? Or should
I was not able to
Right,
hear it.
so I
If you
think
could repeat
the
it.
question was,
Oh, we can't hear you though. We can't hear
Sarah,
Sarah right now.
but I think the question was, let me repeat the question, and then you can increase the volume there so everyone can
So
hear
one of
you.
the
I think
participants
the question is,
the-
what are the economic aspects of this technology? How do we see this have an impact from the economic point of view? And maybe you can comment on that a little bit, Sarah?
Yeah, so I guess like thinking about the quantum computing systems from an economic point of view, in one realm of economics, you do have this ability to do financial modeling and forecasting. And so I think in that realm of economics, there's obviously an impact there with how we can improve how we do budgeting and forecasting. But then of course, on the economics of scaling these systems, how much they cost, like what power they consume, I think, you know, today's supercomputers are extremely powerful, but they have massive, massive computational power suck that they pull in. And so I think it's hard to make an analogy between like number of qubits or algorithmic qubits, whatever you want to define, and like an analogous parameter in a classical system. But I think the power of quantum and like the economics and how it scales is really that once you have the architecture in place, if it's a scalable architecture and you can continue to add high performance qubits to it, you can get increases in computing power at very, very low cost, especially if you can network them together between systems. And so ultimately that's the goal and the roadmap of what we're doing at IonQ. And so I hope that answers your question, like in the economics, and that there are impacts to the financial industry with modeling, but then also with the right architecture, scalability, and the performance and cost side is highly favorable.
I can go. Hi, Sarah. Thank you so much for your presentation. My question is, how do you think quantum computing can be used for, let's say, like particle physics or like quantum physics research?
Yeah, that's a great question. And I think, so again, like I do want to give a disclaimer that like my my applications at IonQ are not as much on the theory and the application side, but I think in your question about modeling quantum physics and doing those types of simulations, I think that the similarity there is in how there are benefits to the pharmaceutical industry and this battery solver where you can simulate quantum chemistry with truly quantum mechanics. And so I think there could be similar benefits if, you know, there are algorithms or problems that need to be set up on the quantum physics side of things to actually have that running on a system that can purely replicate those behaviors. I think that would be a huge benefit. I don't have specific examples of like quantum mechanics applications in mind, but I think quantum chemistry simulations are a derivative of that. And I think are, you know, you have a lot of benefit from being able to do those types of computations on a system that can fundamentally replicate how the behavior is.
Yeah, if I can add to this a little, my name is Joel Gottlieb and I'm from QCI. There was some work done actually at Purdue University a couple years ago with a group in the physics department at tracking particle tracks through a particle detector. In that case, they used the D-Wave quantum computer, but the IonQ quantum computer would be just as perfect of a machine to try those problems on. So I think that's what you've hit on there is it's a research area that's coming, and we're actually looking for, everybody's looking for applications. So maybe you yourself will be able to apply one of those. These machines are all good for this kind of work.
Yeah, thanks, Joel, for adding that. Great context.
I think we have another question.
So I was just curious about like how you use lasers to connect the ions and have entangle them.
Yeah, that's a great question. So, and I can speak to this more so than some of the applications questions on like the physics and optical side of things. So basically what you have when you're entangling information states between qubits is like, let's imagine a chain of 4 ions and you shoot lasers from both directions at those 4 ions. And the interference pattern basically is set up and programmed in a way to excite to tune the spin of the ion to have it go from its like ground state to its excited state. And there's a very repeatable path between the ground state to the excited state and back. And basically what happens when you address 2 ions at the same time is that you introduce these micromotions and these energy states with the ions. And at the quantum level, the information state between entangling both of them with the laser beams at the same time allows the information to be held. And that's kind of where I will be totally honest, like my ability to get deeper into an explanation of the quantum physics side of things definitely tapers off. But essentially what you're doing is you tune lasers specifically to move the ions from their ground to their excited state. And then the micromotions and the energy that's held by both of them are tied together. And so that is how, at a high level and without a PhD in atomic and molecular physics, how the entangling works.
I just wanted to
Maybe I
add,
just comment a little bit on that as well. So when you have these ions are electrical particles, they are charged, right? So this Coulomb interaction, they talk to each other, right? So there's also these optical transitions as well. So by exciting the ion, and also by exciting the ion, you are changing the energy level of the ion, right? At the same time, you give the ion a kick because it absorbs a photon, right? If the ion moves, it grabs the other ions with it. So it's kind of, there's this interaction that if something happens to one ion, the neighboring ions would feel it. So that's how we can roughly understand where this entanglement comes from. But I'm happy to stay around and like talk on the whiteboard a little bit more on that.
and I wanted to add one more
Any
thing.
other question from the audience in the room? And then maybe we can take 1 question or 2 questions from the Zoom as well. Sure, yeah, maybe.
Can I make one point for Sarah, for the students, if I might?
Okay, so Sami Alajluni asked that question. So what is the typical IonQ system size for the same computational power? What is the size different compared to classical computers?
Yeah, so that, are you guys able to hear me okay? Okay, excellent. So I saw that question in the chat, and that's a great question. And it's hard to kind of answer in terms of like, what is the size difference compared to classical computers? Because obviously you have supercomputers, you have laptops, you have high performance PCs. The size difference, I think, so on our website, we have a picture of kind of like where we're scaling technology and how big it is now and how small we expect to get. And there's an image that shows the representation of like a person standing next to the system. And so roughly I'd say like that enclosure that I showed of one of our systems in the lab at College Park, it's roughly, I would say 8 feet tall, to give you a sense of scale. For confidentiality reasons, can't explicitly say the exact dimensions, but it's a big box that a person stands up and is like, maybe 70% of the height of that box. And then comparing the computational power of like what we have now versus an analogous classical system, that one is tough to answer. I know there was some exchange in the chat about this, and I'm happy to look into that more and maybe get back to the person who asked the question, unless of course Joel or Madi or anyone that was chiming in about this in the chat wanted to kind of give their context.
That's a really hard question.
Thank you so much, Sarah.
Yeah.
Thank you so much. I think this was really great, and I think we all enjoyed your presentation, and we hope to kind of be in touch, and hopefully it would be, if the students have any questions, I hope you don't mind that they would reach out to you. And
yeah, please. Yeah, my email is my last name @ionq.com. So you guys can reach out to me there if you have any follow-up questions. But yeah, thanks again for this opportunity and for everyone for tuning in and asking great questions.